FACS is generally a power electronics-based system. FACS is a collection of controllers. FACS helps to improve power enhancement capability. FACS controller controls series impedance, shunt impedance, current, voltage, phase angle, etc. Transmission line involve the combination of mechanical and FACS controller. High power transistor or thyristor is the basic element of power electronics. FACS have high speed reliability of switching. A flexible alternating current transmission system, FACS, is a system composed of static equipment used for the AC transmission of electrical energy. It is meant to enhance controllability and increase power transfer capability of the network. It is generally a power electronics-based system. FACS is defined by the IEEE as a power electronic-based system and other static equipment that provide control of one or more AC transmission system parameters to enhance controllability and increase power transfer capability. According to Siemens, FACS increase the reliability of AC grids and reduce power delivery costs. They improve transmission quality and efficiency of power transmission by supplying inductive or reactive power to the grid. Shunt compensation. In shunt compensation, power system is connected in shunt, parallel, with the FACS. It works as a controllable current source. Shunt compensation is of two types. Shunt capacitive compensation. This method is used to improve the power factor. Whenever an inductive load is connected to the transmission line, power factor lags because of lagging load current. To compensate, a shunt capacitor is connected which draws current leading the source voltage. The net result is improvement in power factor. Shunt inductive compensation. This method is used either when charging the transmission line, or, when there is very low load at the receiving end. Due to very low, or no load, very low current flows through the transmission line. Shunt capacitance in the transmission line causes voltage amplification, Ferranti effect. The receiving end voltage may become double the sending end voltage, generally in case of very long transmission lines. To compensate, shunt inductors are connected across the transmission line. Examples of series compensation. Static synchronous series compensator, SSSC. Thyristor-controlled series capacitor, TCSC, a series capacitor bank is shunted by a thyristor-controlled reactor. Thyristor-controlled series reactor, TCSR, a series reactor bank is shunted by a thyristor-controlled reactor. Thyristor-switched series capacitor, TSSC, a series capacitor bank is shunted by a thyristor-switched reactor. Thyristor-switched series reactor, TSSR, a series reactor bank is shunted by a thyristor-switched reactor. Examples of shunt compensation. Static synchronous compensator, STATCOM, previously known as a static condenser, STATCON. Static VAR compensator, SVC. Most common SVCs are thyristor-controlled reactor, TCR. Reactor is connected in series with a bidirectional thyristor valve. The thyristor valve is phase-controlled. Equivalent reactance is varied continuously. Thyristor-switched reactor, TSR, same as TCR but thyristor is either in zero, or full, conduction. Equivalent reactance is varied in stepwise manner. Thyristor-switched capacitor, TSC, capacitor is connected in series with a bidirectional thyristor valve. 5 thyristor is either in zero, or full, conduction. Equivalent reactance is varied in stepwise manner. Mechanically switched capacitor, MSC, capacitor is switched by circuit breaker. It aims at compensating steady-state reactive power. It is switched only a few times a day.